Let's turn to NASA's Artemis spacecraft next. It has finally arrived at the moon.
NASA's Artemis spacecraft has begun its first orbit of the moon.
Exceeded expectations since last week's launch.
Imagine standing on the edge of a discovery so monumental, it could reshape humanity's future in space.
In a few years, this is a game changer.
4 billion years ago, a colossal impact struck the moon's south pole, carving the South Pole Aitken Basin, the largest and deepest crater in the entire solar system. Beneath its surface lie untouched materials: thorium, rare earth elements, iron-rich deposits and primordial compounds that predate every civilization on Earth. These remain exactly as they were when the moon was still cooling, preserved by deep cold and cosmic silence. NASA's Artemis III astronauts are preparing to land directly above these deposits, not just for scientific discovery, but for strategic, economic and geopolitical dominance. What you're about to learn may challenge everything you thought you knew about lunar exploration. Who will control these resources? And what will it mean for life on Earth? Before we dive in, hit subscribe. You won't want to miss the revelations from this mission. The ancient excavation nobody expected, the South Pole Aitken Basin, or Spie Basin, formed during the moon's pre-Nectarian epoch, a time when the moon was still cooling from a molten state. A massive impact over 4 billion years ago created the deepest excavation ever recorded on the moon. The impact punched through the lunar crust, exposing materials from the lower crust and upper mantle. Among these materials are creep-rich liquids, potassium, rare earth elements, and phosphorus, representing the moon's final chemical differentiation. Thorium can enable next-generation nuclear energy. Rare earth elements are essential for electronics and defense technologies, and iron-rich minerals could support future lunar infrastructure, subsurface structures, and natural habitats. NASA's Grail mission uncovered massive subsurface anomalies, extending up to 500 kilometers with no surface expression. These structures are likely density variations and voids created by the immense stress of the SPA impact. Radiation is the greatest threat to long-term lunar habitation. Unlike Earth, the moon has no protective magnetosphere or thick atmosphere. Solar particle events, SPEs, and galactic cosmic rays, GCRs, continuously bombard the surface. Subsurface voids provide natural radiation shielding, stable temperatures, and protection from micrometeorites. The moon's natural infrastructure reduces engineering challenges and enables sustainable, long-term presence. Water ice, the catalyst for lunar expansion. Water ice discoveries transformed lunar strategy. The L-Cross mission confirmed water ice concentrations of 5.6% by mass in permanently shadowed regions like the Cabeus crater. These are not small pockets. They are large, concentrated resources. Water serves multiple purposes. Rocket propellant split into hydrogen and oxygen for high-thrust missions, life support for drinking water and breathable oxygen, and agriculture for sustainable lunar farming. The South Pole's deep shadows preserve volatiles below 330 degrees Celsius. However, the terrain is extremely porous and unstable, making landings hazardous. Space agencies use ground-penetrating radar, GPR, to map regolith layers, identify ice deposits, and determine safe landing zones. Whoever maps and secures these resources first will dominate the next era of lunar expansion. Should humanity prioritize exploiting lunar resources, or should the moon remain a shared heritage of all mankind? Economic and strategic value of lunar resources. Speculative estimates place the moon's resources at over $1 quadrillion. This includes helium-3 for future fusion reactors, rare earth elements critical for electronics, defense and renewable energy, metals for space-based manufacturing, and water for fuel and life support. These immense resources triggered geopolitical competition. India's Chandrayaan-3 landing highlighted international urgency, while China's Chang'e missions advance rapidly. Nations racing to control lunar resources gain asymmetric advantage, from infrastructure knowledge to operational control for deep space expansion. The moon is no longer just a scientific curiosity, it is a strategic commodity. Any delay could result in dependency on competitor-controlled supply chains, mirroring Earth's rare earth vulnerabilities. Ethical and environmental considerations. NASA operates under a mandate to benefit all humankind, yet concentrated lunar resources raise ethical challenges. Public engagement, transparent policies, and participatory assessments are essential. NASA frames resource utilization as enabling exploration, not exploitation, ensuring ethical and strategic alignment. Citizen science programs, astronaut-captured media, and public access to mission data maintain democratic legitimacy while establishing preemptive frameworks for resource claims. Artemis III. Mission objectives. Artemis III. Astronauts will land directly on the SPA ejector field, collect samples from primordial deposits, deploy instruments to analyze subsurface structures and volatiles, and validate resource concentration for strategic viability. Even if initial concentrations are lower than predicted, the geological confirmation ensures continued strategic competition. Unlike terrestrial mining, lunar resources are unique. Any viable concentration justifies further development. The urgency and global lunar race. NASA emphasizes long-term strategy, resilience, and goal-oriented planning. The moon is now contested territory, where early movers gain decisive advantage. 4-billion-year-old deposits, trillion-dollar valuations, and international competition create unparalleled urgency. The nation establishing a permanent lunar presence first will dominate resource access, infrastructure, and future deep space expansion. This is more than exploration. It is strategic geopolitics in orbit, determining terrestrial and extraterrestrial industrial supremacy. Future of lunar colonization. Subsurface voids, water ice deposits, and primordial materials combine to make the South Pole the ideal location for human settlement. Advanced mobility systems, drilling technologies, and GPR mapping allow safe and sustainable colonization. Permanent lunar bases are no longer science fiction. They are inevitable. But this raises questions. Who governs the moon? Who benefits? And how do we prevent monopolization? NASA is preparing the public to accept a shift from exploration for knowledge to strategic resource development. Ethical frameworks, international collaboration, and transparent public messaging are central to maintaining legitimacy and preventing conflict. The new space race, USA versus China. The modern space race is no longer about planting flags. It is about securing resources that could define the next 1,000 years. The United States is pushing aggressively with Artemis, but China is rapidly closing the gap. China's Chang'e 7 and Chang'e 8 missions aim to land at the lunar South Pole before 2030. Their goal? Build a permanent international research base and secure access to water ice, rare earth elements, and thorium-rich deposits. China has already completed sample return missions, rover deployments, and established relay satellite networks to maintain communication with the moon. Modular power stations, extraction rovers, and 3D printed regolith structures are already under development. The United States counters with the Artemis Accords, an international agreement that outlines rules for lunar resource use, safety zones, transparency, and peaceful operations. However, China and Russia have not signed these accords, raising the possibility of contested territories and competing no-go zones on the moon. Military and strategic implications of lunar bases. The moon provides a strategic vantage point unmatched on Earth. It offers line-of-sight access to the entire planet, ideal for monitoring satellites, early warning systems, deep space communication arrays, and surveillance operations. Control of the South Pole means dominance over key communication relays, navigation systems, and critical space infrastructure. While international treaties prohibit weapons of mass destruction on the moon, nations understand the moon's economic and strategic leverage. The US Space Force considers lunar infrastructure vital to securing national interests. China's military documents explicitly state that space is the commanding height of future warfare. The moon's infrastructure could support electronic warfare, missile tracking, advanced reconnaissance, and satellite defense without violating international law. The economic and technological dominance achieved through lunar control could be as effective as military deployment, providing global leverage without firing a single missile. Lunar economy. Trillions in resources. The moon's resources could exceed the total value of Earth's mining industries combined. Water ice becomes hydrogen and oxygen fuel. Helium-3 offers potential for clean fusion energy. Rare earth elements power electronics, defense systems, and renewable energy technologies. Titanium, aluminum, and iron extracted from regolith can build habitats, solar arrays, and industrial facilities. Silicon harvested from lunar soil could produce vast energy networks for both lunar settlements and orbital satellites. Over the next 50 years, a complete lunar economy may emerge, including fuel depots, mining operations, industrial hubs, research stations, space-based solar energy farms, tourism, and even cryptocurrency ventures based on space resources. This economic expansion will redefine global wealth and power distribution. Developing nations are forming partnerships to participate, ensuring they are not left behind in the lunar revolution. Private investors are preparing funding dedicated solely to lunar resource extraction and infrastructure development. The urgency of Artemis and future missions. NASA publicly frames Artemis as a scientific and exploratory mission, but internally, the urgency is driven by geopolitical competition. The US knows that controlling the lunar South Pole equates to dominance in future space operations. Artemis III, IVA, and V aim not only to return humans to the moon, but to establish the first commercial extraction systems, fuel depots, permanent habitats, and operational infrastructures. Success on the first Artemis landing offers the United States a strategic advantage lasting decades. Partnerships with private aerospace companies, SpaceX, Blue Origin, Astrobotic, accelerate these goals. Robotics, autonomous mining, and sustainable habitat construction are all being developed in parallel to ensure American primacy. Lunar colonization, the next chapter. For humanity, lunar settlements will develop in a predictable cycle. Robotic exploration, construction of infrastructure, energy systems, extraction of ice and minerals, expansion into subsurface voids, and eventually permanent cities. These cities will rely on local resources, solar energy, nuclear microreactors, and regolith-based radiation shielding. Life support systems will be managed by AI, hydroponics, and closed-loop agricultural systems. The moon will become humanity's first extraterrestrial home. Children may one day be born in low gravity. Universities, research centres, and commercial hubs will flourish. Lunar governance becomes a question of global law. Is it under nations, corporations, or humanity as a collective? Who decides property rights, resource allocation, and conflict resolution on a celestial body? Ethical, political, and economic frameworks must evolve alongside technology to prevent monopolization and conflict. Ethical and environmental considerations. The moon is not just a resource, it is a historical and environmental treasure. Action of water, minerals, and helium-3 carries ethical implications. Environmentalists warn of irreversible damage to ancient craters formed over billions of years. Philosophers caution against repeating patterns of colonial exploitation. NASA's mission planners advocate responsible use, public data transparency, international collaboration, citizen science programs, and clear frameworks for resource allocation. Balancing ethical stewardship with strategic necessity will determine whether humanity develops the moon responsibly or repeats Earth's mistakes on a planetary scale. Technological innovation and infrastructure. Technology will drive lunar colonization. 3D printing with regolith allows rapid construction of habitats, radiation shielding, and solar towers. Ground-penetrating radar identifies safe tunnels and ice deposits. Autonomous rovers conduct mining and transportation. Solar farms atop crater rims provide uninterrupted power. Nuclear microreactors offer redundancy during shadow periods. The combination of robotics, AI, and advanced engineering allows humanity to live sustainably in extreme conditions. Over time, lunar settlements may become self-sufficient, exporting fuel, materials, and energy to Earth and other space missions. The moon becomes a hub for interplanetary expansion. The global implications of lunar control. Whoever controls the moon controls the future of energy, technology, defense, and space travel. Resource monopolization can provide a nation with unmatched technological leverage. The moon's helium-3 could power clean energy grids. Rare earth elements reduce reliance on terrestrial supply chains. Water ice supports long-term habitation and interplanetary logistics. Military, industrial, and scientific superiority converge in this celestial frontier. Countries, private companies, and international alliances are already negotiating lunar cooperation agreements. The outcome of these agreements will shape global politics for decades. The next 20-50 years, by 2045, permanent bases on the South Pole will likely exist. Commercial mining of water ice, helium-3, and rare earth elements will begin. Fuel stations for Mars missions will operate. International research colonies will thrive. Large-scale solar farms and underground habitats will emerge. Lunar cities will feature greenhouses, laboratories, manufacturing hubs, and AI-managed infrastructure. The moon will evolve from a mysterious satellite to a fully functional, off-world civilization. Humanity's presence in space will expand exponentially, leveraging resources, technology, and energy for planetary and interplanetary advancement. Humanity stands at the beginning of its greatest transformation. The question is no longer whether we should return to the moon, it is whether we can afford not to. The nation, corporation, or alliance that secures the lunar South Pole first will shape space exploration, technological supremacy, and global economic power for centuries. The moon is no longer a distant dream. It is a strategic, economic, and existential imperative. Artemis III and all future missions mark the start of a new era, a future where humans live, work, and thrive beyond Earth. The moon waits. The question is, who will take it first and what legacy will they leave for humanity?